Hi folks, welcome back to another lesson, and hopefully some of this stuff will be familiar to you because I'm sure we covered this in S3. So we're now starting radiation, and basically this is introduction to radiation. So we describe the structure of the atom, which then leads to the description of radioactive decay. We're going to talk about the different sources of radiation, both natural and artificial, and something called background radiation. And then we describe the three types of radiation that you can find that we're going to talk about in the course. Now, there's going to be a lot of information here, so I'm going to set an assignment to help you organize this information. Okay, so can radiation really make these things happen? Can they, for example, give you superpowers, mutate animals? Can they be used to kill people? So this was a Ukrainian politician who was rumored or believed to be assassinated by the Russians using pollution, not pollution, polonium, which is a radioactive material. And obviously, can we use nuclear radiation as weapons? Okay, so first of all, let's start by looking at what causes radiation. And to look at that, we need to look at the atom. So we expect you to know that the atom is made of an electron, which is a negative charge, a proton, which is a positive charge, and a neutron, which has zero charge. And if you're taking notes in your assignments, I would like you to make a note of the three different types of particles that make up an atom, the charge that each of these have, and also the position of each of these elements in an atom. Okay, now the nucleus is the center of the atom, and it's made up of neutrons and protons. And if you've done chemistry, you'll be fairly familiar with these concepts. Okay, now to give you an idea of the size of the gap between an electron and the nucleus, if we were to draw it to the scale of a golf ball, then if the electron was the size of a golf ball, that golf ball would have to be 1.5 miles away before you reach the nucleus. So the really weird thing about atoms is that the majority of the atom is actually made of nothing. Because remember, atoms make up everything, so within an atom, you can't have anything between the electrons, protons, and neutrons. Okay, now just give you an idea of some of the important people who did a lot of work to discover what radiation was. Two really important names, Marie Curie, which you might have heard of from the Marie Curie Foundations, and Henri Becquerel. Becquerel we're going to use as a unit for radiation. And they both won a Nobel Prize in 1903 for radioactivity. And unfortunately for Marie Curie, because she was working with radiation quite a lot, and they probably didn't understand the dangers of it, she actually died of cancer later in life. Okay, so what is radioactive decay? Well, radioactive decay comes from atoms, and it happens when an atoms become unstable. And when this happens, they break apart, and we call this a decay. And when it decays, you get new particles being formed and radiation being released. So this is where radiation comes from. So the formal definition is that radioactive decay is a disintegration of an atom releasing energy. So this is something that I want you to take down in your notes. Okay, now there are lots of different types of radiation. So one of the most common one is something called the background radiation. And it's called the background radiation because it's always around us. And one of the causes of this background radiation is the Big Bang. Okay, physicists believe that there was an event called the Big Bang. It wasn't an explosion, it was just something that happens. And as a result of this, a lot of energy was spread out across into space, or space was created as well. And one of the upshot is that some of that energy is still left over, and it forms what we call the background radiation. And you can detect this using a Geiger counter, which we're going to look at later on. Okay, other sources of background radiation can be from natural or artificial sources, and that's how we generally group them. There's a nice wee video there. I'll put that in a separate file so you can watch that, and it tells you just a little bit about background radiation. Again, I'd like to remember this because background radiation we're going to come back to when we do an experiment called half-life. Okay, so what are the natural sources of radiation? So these are caused by things that happen in the world around us, and so we call them natural. And again, you just need to remember them. You can get them from cosmic rays, animals, rocks, soils, and plants. Now, rocks in particular can release radioactive particles. So, granite is a really well-known producer of radioactive uh, uh, materials called radon gas. So, for example, Aberdeen, which is called the Granite City, has generally a slightly higher background radiation because of there being more granite in the city, and therefore that granite will release radon gas, which can be radioactive. Okay, animals and plants are radioactive themselves because they absorb radioactive elements from the air around them. So one of the classic ways to kind of let people think about radiation is bananas. Bananas are slightly radioactive because they contain positive potassium ions, and that can be slightly radioactive. Now, just because they're radioactive doesn't mean they're going to give you cancer. You don't get cancer like a disease. You get a chance of developing cancer. So what these things do is that if you expose yourself to a really high dose of radiation, and we'll look at that later on, you have an increased risk of getting cancer. So these things exist naturally, so we're quite used to these. It's not like they're going to give you cancer or increase your risk of getting cancer. What's more likely to increase your risk of getting cancer are artificial sources of radiation. And these in general are sources that are made by human beings. So again, I'd like you to note down these three types of artificial sources: nuclear weapons, nuclear power, and X-rays. So these, if you get too much radiation from these, you can be at serious risk of developing cancer. So for those reasons, that's why you're only allowed to have so many x-rays per year. So if you've ever been to an x-ray, they will ask you, have you had an x-ray before this year? Or have you had any other exposure to radiation? So for example, if you fly quite a lot because you're higher up in the atmosphere, then you're more likely to be exposed to greater amounts of radiation. So again, there are limits to this. If you work in a nuclear power station, you'd obviously monitor how much radiation you're being exposed to, because again, as I said, the more radiation you're exposed to, the greater risk of developing cancer. And of course, later on, we're going to talk about Chernobyl, one of the worst nuclear power station disasters, which you probably might have read a little bit about because there's a really interesting drama series on Sky quite recently. Okay, now let's move on or zoom in and look at the three different types of radiation. And again, I'm afraid a lot of this is just information you need to know. Some of it you might remember from third year because we did a nice activity on this in S3, but hopefully you can just kind of write these down and just learn these kind of off by heart. So the first particle we're going to look at, and as a particle, is something called an alpha particle. And this is a symbol for the alpha particle. It's like the SNP symbol sitting on its side. It's made up of two protons and two neutrons, and essentially it's a helium nucleus. So remember, helium is an element that has two protons and two neutrons with the electrons removed. Because it's just got two protons and two protons are positive charge, the neutrons are neutral, so helium or alpha particles rather are positively charged. It's got three different symbols which I would like you to recognize. This one here and this one are the two most commonly used, so make sure you know that. It has a very, very short range, and it's the largest of all three types of radiation. And by largest, I mean physically large because it's literally made of physical particles, two protons and two neutrons. And as you'll see later on, the other ones are made up of smaller things. So lots of information to remember. As I said, the assignment will help you to organize this information. Okay, the next type of radiation is beta radiation, and it has the following symbols. So this is a Greek letter for beta, and again, the one we'll probably use the most is this one here. Okay, beta radiation is made from it's very, very small, and this is because it's made from electrons. Okay, in fact, it's a beam of electrons. So again, if you remember this, okay, it's negatively charged because remember electrons are negatively charged, and these electrons are given out in something called a beta decay. You don't need to know too much about this. I've just include that for further detail. And generally we describe it as a fast moving high energy electron released from the nucleus. and it has a medium range compared to alpha radiation. And because beta radiation is a flow of electrons, you can see why alpha is the biggest of the three radiations. Certainly it's bigger than beta. Okay, the final type of radiation is called gamma, and the symbol for gamma is like this. It's kind of like a Y with a curly tail, and it's electromagnetic wave. So it's not made out of particle, it's actually a wave, so therefore it's neutral. It has the greatest amount of kinetic energy because it's a wave moving through the atmosphere or through space. It is high frequency electromagnetic waves, so it travels at the speed of light. So remember that from electromagnetic spectrum. And in general, it's the gamma part of the electromagnetic spectrum. There's no significant mass and it has the greatest range. So compared to beta and alpha, because it's a wave, it's not made up of a particle like beta or alpha, it has no mass and it also has the greatest range. And as I said, the symbol for gamma is it's like a curly Y. This is how we usually write it. Okay, now, how do we control this radiation? Because if you've ever been for an X-ray or even a CT scan, that uses radiation. And generally, those type of radiations that we're talking about will be controlled by electric fields. Okay, so what we have is we've got two metal plates, one which is positively charged and one which is negatively charged. And there'll be an electric field existing around this that I'm not going to draw on. But you could imagine if we have an alpha particle, and if we shoot the alpha particle in at the middle, so remember this is symbol for the alpha particle, remember the alpha particle is positively charged, so I'm just going to put a wee plus there to remind you of that. So as it moves in, what do you think is going to happen to this alpha particle? Well, if we look at the plates, one is positively charged and one is negatively charged. So if the alpha particle is positively charged, it's going to be attracted to the negative plate, isn't it? Because remember, opposites attracts when it comes to charges, and like will repel. So not only will the alpha particle be attracted to the negative plate, it will also be pushed or repelled by the positive plate. And so the path it will take will look like this. Okay, oops, trying to draw this a wee bit better. This should really be a curve. So quite tricky as I'm drawing this on the mouse here, so let me tidy it up a wee bit. Now, hopefully, you can kind of see what I'm trying to draw here. Now, if you were able to turn your screen to the side, what kind of shape do you think we're trying to draw here? Pause the video and have a wee think, okay? Hopefully, you're able to tell me that it is a parabola, or at least half a parabola, okay? So you can see we could even tie this in with our projectile motion. Okay, so that's an alpha particle. How do you think a beta particle would travel? So let's just put the beta particle at the bottom because that's where I can fit it in. Now remember the beta particle is negatively charged, so what do you think is going to happen when it goes in between these two plates? Well, if we think about the alpha particle, that was positively charged and it was attracted to the negative plate, then logically the beta particle is negatively charged, so it should go towards the positive plate. And again, it will go in this kind of parabola shape. So once again, I've made a wee mess of that diagram, so let me just draw that again, folks. Okay, so it should go in a parabolic path, remember. Okay, so that's the path of our beta particle, and I'll draw a wee arrow to show you which way it's going. And then finally, if you had a gamma particle, so let's just put the gamma particle at the top here now, how do you think it's going to travel through these two plates? Well, remember, a gamma particle has zero charge, so I'm just going to put a zero there. So it's not going to be attracted to the negative, it's not going to be attracted to the positive, so all it does is it just travels in a straight line through the metal plate. Okay, so make sure you have a wee copy of this diagram and you understand why these three particles take these paths. Okay, final thing I want you to remember is that when radiation passes through a material, the energy from that radiation is absorbed, and the more energy absorbed, the greater the damage done by the radiation. And that's why the more radiation you absorb, then the greater the risk of of developing cancer you will have. Because if you absorb more of that radiation energy, that means more damage has been done to you. That means your cells are more likely to become cancerous. Don't worry about remembering this diagram. We're going to talk about this in the next lesson, but you may remember it from last year. And then finally, this is just a wee summary to show you the types of natural radiation and artificial types of radiation.